Okay, good evening, everybody. Okay, I do want to welcome all of you on a snowy day, on a snowy Monday evening, to another online review session. I do hope that the snow weather has allowed some of you the opportunity to catch up on your studies. And I think the snow is all gone by now, so we should be able to go back to school tomorrow. So anyway, we are going to, today we are going to review for exam number 2, which is scheduled for Thursday, that is March 6th. And so for this review session, we are going to use the exam number 2 that was given in the spring of 2013. I do hope that you guys have a copy of that exam with you. So what I want to do to start the session, I will go through the questions numbers 1, 2, 3, and 4, because those questions give us an opportunity to review the reagents and what the reagents do. And then from numbers 1 to 4, I will go to number 10. Okay. I also noticed that a lot of you have joined us, so during the course of this session, I will be acknowledging each one of you. Okay, to get the session started, Mashake, can you go ahead and read this for us?
Provide the missing reagents in the following synthetic schemes.
Okay, very good. But before you go though, let us see here. We need to provide the missing reagents for the following synthetic scheme. I do need your assistance in doing a couple of them. Okay, here we want to go from a ketone to a tertiary alcohol. So what reagent do we need right here?
The methyl grignard followed by the hydronium ion.
Okay, very good. So you want to do a Grignard reaction here. So you want to use methyl magnesium Grignard, okay, methyl magnesium bromide. So you want to use a Grignard reagent, and then you follow that up with hydronium ion. Excellent, that is correct. Folks, you notice here, whenever you do a Grignard reaction, you have to do the Grignard reaction as the first step, and then you follow that up with the addition of the hydronium ion. These have to be 2 separate steps. In other words, you have to indicate step 1 and step 2. And you can see here also the Grignard is used to transform a ketone to a tertiary alcohol. Okay, in this particular instance, we are making a new carbon-carbon bond, so we are attaching this carbon here to this carbon. Okay, Mashake, about the next one, B. We want to go from this tertiary alcohol to a carbon-carbon double bond to an alkene. What reagent do we need here?
You could use sulfuric acid or POCl3.
Okay, excellent, excellent. So we could use sulfuric acid, or in this case, you could also use dilute acid, which is hydronium ion. Okay, or we could also use, we could also use phosphorus oxychloride. Okay, excellent, very good, and thank you. Okay, now I'm going to open the floor to the rest of you. Now, at this point, we want to go from a carbon-carbon double bond to an epoxide. This is an epoxide. Okay, does anybody know what reagent we need here? You could go ahead and send it to me through the text message. Okay, excellent, excellent. Okay, Victoria Larson, you are welcome. Okay, that is correct. MCPBA, Alexis, MCPBA, MCPBA. That is correct. In other words, you want to use this MCPBA, which is this molecule here. So we call this molecule M-chloro benzoic acid. So that is how we got the acronym MCPBA. Very good. And this reagent here is an excellent reagent for converting a carbon-carbon double bond to an epoxide. Very good. Okay, now we want to go from the epoxide to a diol. And we want to form a trans-diol. Now, what reagent do we need here to go from an epoxide to a trans-diol? Okay, very good. Excellent. So you guys say we need hydronium ion. Okay? So therefore, if you have an epoxide and you want to open the epoxide, what you need to use is a dilute acid. The dilute acid will open the epoxide in such a way that the two hydroxy group, this here and this here, will be trans to each other. Okay? So therefore, the combination of MCPBA followed by hydronium ion, what they do is to introduce two hydroxy groups across the carbon-carbon double bond such that those two hydroxy groups will be trans to each other. Okay? Very good. Okay, so far so good. So let us now do E. Okay, we want to do C right here. Okay, what reagent do we need for this? At this point, we want to make an ether. Notice what we are doing here. We are forming a bond between this oxygen and this carbon, replacing this hydrogen here with a methyl group. Okay, so what reagent do we need here? Anybody has an idea? Okay, I see Alexis. Okay, very good, excellent. So sodium hydride followed by methyl iodide. Excellent, excellent. Okay, so therefore we say step 1, keep in mind, say step 1, sodium iodide followed by an alkylating agent. This time the alkylating agent is methyl iodide. Now, so what happens here, anytime you have an alcohol and you have sodium iodide, what it does, the hydride of the sodium iodide will act as a base, and in so doing, what it does is to abstract the proton from the alcohol or grab the proton from the alcohol such that you are now going to leave a pair of electrons with this oxygen here. So therefore you get this alkoxide. Okay, you get this, plus hydrogen gas is formed, this hydrogen gas. Now this alkoxide that you form now could now react as a nucleophile in an SN2 reaction. If you have any alkylating agent, it could be, as long as it is a primary or secondary alkylating agent. And what do we mean by that? In other words, you have a carbon that is attached to a good leaving group, and that carbon should be a primary carbon, just as this here, or it could be a secondary carbon. In that case, we will form an ether, which is this here. Okay, and that is what we have here. This sodium hydride will remove the hydrogen from this alcohol, from the alkoxide, similar to this one here, and then the alkoxide will now, once we now introduce a methyl iodide, you are now going to get what we call an SN2 reaction. you get an SN2 reaction. Okay? Okay, very good. So we have finished this. So let us go to the next one. As a matter of fact, let me jump a little bit and get... Alexis, can you read this for us? Number 3. We'll go back to number 2.
Fill in the missing reagents for the following transformations.
Okay, very good. But before you go, though, I do want you to give me some assistance. Okay, if you take a look at the first reagent, what are we doing here? What are we doing in the first reaction here?
Converting a ketone to a secondary alcohol.
Okay, excellent. We are converting a ketone, the carbonyl of a ketone, to a secondary alcohol. So what reagent do you think we need here?
Step 1 would be sodium borohydride, and step 2 would be the hydronium ion.
Okay, excellent. So step 1, you want to use sodium borohydride, and then you follow that up with hydronium ion. Folks, once again, you see here, these are 2 separate steps. You have to indicate step 1 and step 2. Because I noticed in the past, a lot of you simply write sodium borohydride and hydronium ion. You do not indicate the steps. In that case, you lose a lot of points. Okay, so that is correct for this. This reagent here would transform the carbonyl of a ketone to a secondary alcohol. It could also transform the carbonyl of an aldehyde, in that case, to a primary alcohol. So if you take this generic aldehyde here, and you use the same reagent, sodium borohydride, followed by hydronium ion. In this case, keep in mind what sodium borohydride is doing, followed by hydronium ion. You are in essence adding 2 hydrogen atoms across the carbon-oxygen double bond of a ketone or aldehyde. In this particular instance, we are going to form a primary alcohol. Okay? So sodium borohydride reacts with an aldehyde to form a primary alcohol. On the other hand, it reacts with a ketone to form a secondary alcohol. Okay, finally, before I let you go, Alexis, okay, number 2, reagent, what do we need for this transformation here? We want to go from the secondary alcohol to this alkyl halide.
You use thionyl chloride, SOC.
What? Okay, very good. So we are excellent, excellent. So you want to use thionyl chloride, which is SOCl2. That is thionyl chloride. Folks, I am hoping by going through this, you are familiarizing yourself with some of these reagents, because keep in mind, I keep telling you, you got to know the reagents in organic chemistry. These reagents are the ABCs of organic chemistry. If you don't know your reagent, you cannot do organic chemistry. Okay, so in this case, we are going to use thionyl chloride. Okay, thionyl chloride will convert an alcohol, in this case a primary alcohol or a secondary alcohol, to an alkyl chloride. Okay, so at this point, let me open the floor to the rest of you. So now we want to go from this secondary alkyl chloride to a Grignard reagent. So what do we need here? Okay, send me a text message. Okay, magnesium. Okay, Erin said magnesium and ether. Excellent, excellent. Victoria Lassen said magnesium and ether. Excellent, good. So all you need here is magnesium and ether. So you see how easy these problems are once you know your reagent. Okay. About number 4. Number 4, we want to react this Grignard reagent here with some reagent in order to give this ketone. Okay, nitride, excellent, excellent. Okay, that is another reagent you need to know of. Okay, keep in mind, let us do some analysis here. this part of the molecule, right here is this right here. Okay, and this is one of those cases in which you want to know your reagent. A Grignard reagent will react with a nitrile to form a ketone. Let me take this off. A Grignard reagent, let us use a generic Grignard reagent. Okay, let us say we're using a generic Grignard reagent. If you have a a nitrile, generic nitrile, and you have a Grignard reagent, let us use a specific Grignard reagent. Let us say we take this. Step 1, and then you follow that up with hydronium ion. Step 2. What this Grignard reagent will do is to convert this carbon here to carbonyl of a ketone, and then this methyl group will be added to this carbon. Of course, we are going to lose nitrogen here. Okay, so this is the product. Okay, so you can see here, this Grignard now, the Grignard alkyl group is this right here, and this carbon here of the nitrile becomes the carbonyl of a ketone. Okay, so therefore, I believe Victoria told us that we need to use a Grignard here. So therefore, your Grignard must be, we need to use a nitrile. So therefore, your nitrile must be that in which the nitrile is attached to the benzene ring. Okay, so very good. So let us go ahead and do that. So you need to use a nitrile. Number 4 will be nitrile, which will be this here. So you use that nitrile, that would be step 1, and then you say step 2, and then you follow that up with hydronium ion. Okay, and therefore you are going to get this ketone here. Very good. Okay, so let me take this out. Let us do 5. Okay, can you text me the result of the reagent for 5? What are we doing here? We want to go from a ketone to a secondary alcohol. What reagent do we need here? Okay, what reagent do we need? Okay, sodium borohydride. Okay, LAH. Some people say LAH followed by hydronium ion. Both of those are correct. Very good. Excellent. Excellent. So therefore, here you say we could use sodium borohydride. Step 1, sodium borohydride, and then step 2, hydronium ion. Okay, in this case also, we could also use lithium aluminum hydride to convert a ketone or an aldehyde to alcohol. Okay, so let us see here. So here, we could also use lithium aluminum hydride, or I would say, or step 1, lithium aluminum hydride, and then step 2, and then hydronium ion. Okay, so you could use any one of these to convert the carbonyl of a ketone to a secondary alcohol, or the carbonyl of an aldehyde to a primary alcohol. Okay, very good. Okay, I see a lot of people have joined us. Hopefully I will be able to acknowledge all of you. I see Brittany Galloway is here, and Chelsea Smiley is also here. Okay, about 6. We want to go from this secondary alcohol to a carbon-carbon double bond to an alkene. So what do we need here for 6? Okay, what do we need for 6? We go, okay. Okay, phosphorus oxychloride. Very good. It's a phosphorus oxychloride, okay? Anytime phosphorus oxychloride, this reagent here, will allow you to transform an alcohol to a carbon-carbon double bond, to an alkene. Or in this case, we could also use dilute acid, okay? Okay, very good. So we have done questions 1 and 2. Questions 1 and 3. So let us go back to question 2. Okay. Angelica, can you go ahead and read this question for us? Okay, it's Angelica. Maybe your mic is not working. Frederick, can you go ahead and read this question for us?
Provide reagents for the following sequence of reactions.
Okay, thank you. Okay, so what we want to do here is to provide reagents for the following sequence of reactions. You will see here, this will be similar to what we've done in the previous 2 questions. Just a way of getting you to know these reagents and what they do. Okay, so once again, we are going from a ketone to an alcohol. So what reagent do we need? Oh, okay, Angelica, I see your mic is not working now. Okay, no problem. Okay, so what reagent do we need? We want to go from this ketone here to an alcohol, sodium borohydride, you see? And once you know your reagents, this becomes very, very easy indeed. Sodium borohydride, step 1, and then step 2, hydronium ion. What other reagent can we use here? What other reagent can we use? Oh, little, okay, somebody said, didn't we just do this? No, we did. This is not the same question. They look very similar though. Or LAH followed by hydronium ion. Okay. Now we want to go from an alcohol to an alkyl bromide. What reagent do we need for here? From an alcohol, okay, phosphorus tribromide. Excellent. See, folks, once you know your reagent, most of this becomes very, very easy. You just have to know these reagents and what they do. I keep saying this. Knowing your reagents is like knowing your ABC, okay? You cannot do anything in life without knowing your ABC. Okay, so now we want to go from the alkyl bromide to this primary alcohol. Okay, let me give you a hint here. Notice we are forming a new carbon-carbon bond, okay, and also we are making a primary alcohol. So what reagent do we need here for C? Anybody, just text me, or you may want to pick up the mic, okay? You want to do a Grignard first, okay? Then follow that up formaldehyde. Excellent, excellent, very good, excellent. So you guys say you will do a Grignard, make a Grignard with magnesium and ether. Very good. So once you make your Grignard, then you want to introduce formaldehyde. That is what you guys are suggesting. Then you introduce formaldehyde. Then after you introduce formaldehyde, then you add dilute acid. Excellent. Okay? Okay, that is correct, because now the reaction of a Grignard, in this case, your Grignard will be this here. And that Grignard will simply just react with the formaldehyde to give you step 1 and step 2 to give you a primary alcohol. Okay, and that is this one here. Okay, very good. Okay, now about D, we want to go from a primary alcohol to an aldehyde. Okay, this here, this is the condensed formula for an aldehyde. Okay, what reagent do we need? Okay, Desmartin. Okay, very good. Desmartin or PCC. Okay, Akosua, you are welcome. Danuchika, you are welcome. It's a PCC. Okay, good. So either PCC or Desmartin. Now, these two reagents will transform a primary alcohol to an aldehyde. They will also, incidentally, they will also transform a secondary alcohol to a ketone. Okay, so they do react with secondary alcohol to also give a ketone. Okay, so you could also use PCC here to get this ketone here, or Desmartin. So here, PCC or Desmartin will transform a primary alcohol, in this case, this molecule here, to an aldehyde. Okay. How about now we want to take our aldehyde, we want to go to a secondary alcohol. And in this case, we are also going to make a new carbon-carbon bond. I'll give you a hint here. Notice here, this carbon here is this right here. So therefore, we are going to be forming a new carbon-carbon bond. Okay, so we are joining these two carbons here. So how do we do that? Let me give, okay, anyway, before I go into that, let us see, any answer for this? Does anybody have an answer for this? Okay, you want to use benzyl magnesium bromide, that's Alexis, okay, and Chika say Grignard, okay, all of those are correct. Okay, yes, you are correct. Use a benzyl magnesium bromide with an aldehyde. Keep in mind a Grignard reagent will react with an aldehyde to give you a secondary alcohol. In this particular instance, therefore, this particular instance here, our Grignard will be coming from this part of the molecule. I think that's what you guys are saying, okay? Okay, so therefore, the Grignard will be this here. Okay, so you add the Grignard to the aldehyde, say step 1, and then step 2, you add your hydronium ion. Okay, and therefore you get your secondary alcohol. Okay, very good, excellent, excellent. Okay, so finally on this question here, we want to go from secondary alcohol to an alkene. Secondary alcohol to an alkene. So what reagent do we need here? Okay, phosphorus oxychloride. Excellent, very good. Okay, so you guys say phosphorus oxychloride. That's Shante Smith. Okay, Princess Alinta. Okay, very good. Oh, by the way, Princess Alinta, I hope you got your ID card that I found in the lecture hall. So let me know tomorrow if you got it, or just send me a text message if you got it. I'll send it through one of your colleagues. Okay. So you said that we go from a secondary alcohol to an alkene. What reagent? Phosphorus oxychloride. Okay, very good. That is this here. Or you could also use dilute acid. Okay. Okay, so let us go to question number 4. Okay. Okay, Robin, if your mic is working, can you read this question for us? Okay, maybe Robin's mic is not working right now. Sean Taylor, if your mic is working, can you read question number 4 for us?
Write the missing reagents for the following reaction.
Okay, thank you. Okay, so write the missing reagents for the following reactions. Okay, once again, this is simply testing your knowledge of the reagents. Okay, so for step 1, okay, what type of reaction is this? We are going from benzene to this ketone here. What kind of reaction is this? And what reagent do we need here? Okay, acylation. Okay, Friedel-Crafts acylation. Excellent, Friedel-Crafts acylation. In other words, what you guys want us to do is to do this. Take an acid chloride. Take an acid chloride. The reason why you say that is because you know you want to attach this group to the benzene using the Friedel-Crafts acylation. Okay, and to do that, you take the acid chloride, this molecule here, and then you add to that a Lewis acid. This time the Lewis acids are aluminum chloride. Okay, and this here, the combination of this acid chloride and the aluminum chloride will give you the Friedel-Crafts reaction, in which you are attaching this carbon here to the benzene carbon right here. Okay, number 2. Okay, at this point we want to go from this ketone to an alcohol. I think all of you should know this. Okay, what reagent is this? Ketone carbonate. Okay, sodium borohydride. So you should know how to think about that. Sodium borohydride, and step 1, and then step 2, hydronium ion. Okay, very good. Okay, now we want to now go from the secondary alcohol to a secondary alkyl bromide. What reagent do we? Okay, phosphorus tribromide. Yes, you guys know this, so I think you guys are getting ready for the exam. Okay, so this reagent here will transform the hydroxy of a secondary alcohol or a primary alcohol to an alkyl bromide. Okay, so at this point we want to go from this alkyl bromide here to the Grignard. So what is the reagent number 4? Reagent number 4. Okay, very good. Magnesium followed by ether. Okay, the ether here is acting as a solvent. Okay, okay, very good. So that will give us this Grignard reagent. Now, you now want to, okay, before we react this Grignard reagent with this ketone, now they want you to take this benzene and give this ketone. Okay, so what kind of reaction is this? 7, acylation. Okay, very good. So here, keep in mind, since we want to attach, so this is the hint here, since we want to attach this here to the benzene, that means that the acid chloride will be coming from this part of the molecule. So therefore, we have this here. Attached to the chlorine, that is your acid chloride. So we say that is step 1. I'm sorry, not step 1 here. And you use this with aluminum chloride, okay? Okay, so this acid chloride plus aluminum chloride will give you this acylation here. In other words, you are going to attach this carbon here to the carbon of the benzene to get your product, okay? Now, once you get this ketone here, they now want you to react this Grignard here with this ketone. Now, after they've done that, they say there is a step 5. What is in step 5 right here? What reagent do you need here? Hydronium ion. Excellent. Very good. So now the reagent here is hydronium ion. Very good. And finally, we are going to go from this alcohol here to a carbon-carbon double bond, an alkene. Okay, so what reagent do we need here? Okay, yes, you could use phosphorus oxychloride. You could use phosphorus oxychloride. Or you could use dilute acid. Okay, very good. So at this point, I think we have gone through most of the reagents that we find in chapters 17, 18, and 19. And now let us go to do a synthetic problem. Okay, let me see some of the new people. Okay, Amira Plaskett, you are welcome. Annette Leby, you are also welcome. Okay, let us see here. Somebody, if I have not talked to you tonight, you have not read the question for us tonight, and your mic is working, can you pick up the mic and read this question for us? Anybody?
Provide a synthetic scheme for the following transformation.
Okay, very good. That's Chelsea Smiley. Okay. Okay, thank you. Say provide a synthetic scheme for the following transformation. Okay, so what we want to do here, now this is a synthetic problem. You notice here, when you get to synthetic problem, this is where you have to now begin to use your knowledge of the reagents, and then you begin to now also use some critical thinking. In other words, at this point, we want you to think critically. Okay, but without knowing those reagents, you cannot think critically in organic chemistry. Okay, so therefore, at this point, let us analyze this problem. What do we have here? Let us number this. We have many carbon we have here. Let's say carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. Now, if I was given this problem, I would say, okay, taking a look at the starting material and taking a look at the product. Okay, I would say very well. It would very well mean that this part of the molecule here, this carbon here, that is the first assumption that I will make is coming from here. So therefore, say, okay, this could very well be my carbon 1 right here, 2, 3, 4, and 5. Now, if that is the case, what that also tells me is that right here, I need to make a new carbon-carbon bond. If you look at this, I need to make a new carbon-carbon bond. This here, and this here, this will be new carbon-carbon bond because these were not present in the starting material. So therefore, the first thing I will ask myself is, what are all of those reagents that will allow me to make new carbon-carbon bonds? Okay, so that is the first thing that will come to my mind. So let me go to a new page. Say reagents that make new carbon-carbon bonds. Okay, staff, can anybody give me some? Okay, can you give me just start anybody? Okay, Greenyard. Okay, very good. Greenyard will do it. Okay, any? Okay, okay, Wittig. Very good. Somebody say Wittig. Okay, keep going. Gilman. Very good. Okay, keep going. Any more? Okay, Narika said Gilman. That is excellent. Shante said, give my action. Okay. Okay, about Friedel-Crafts acylation. We just did that. Friedel-Crafts acylation, Friedel-Crafts alkylation. Okay, we could also, some of you may not think about this, we could also have this nitrile. The carbon-nitrogen triple bond, nitrile. Okay, this could also, when it acts as a nucleophile, you could also use that to form a new carbon-carbon bond. So if you have a list of all of this that you already know, and you know that you need to form a new carbon-carbon bond, then you go back and say, okay, if that is the case, let us see here. Which one of those do I need here? Okay, which one of those do I need? Maybe you need more than one of them. Can anybody give me any idea? But keep in mind we want to form a new carbon-carbon bond here. Okay, keep in mind there used to be carbon-oxygen. Okay, okay, very good. You say you want to use a Wittig. Very good. So you want to use a Wittig. Now we also say here, if you form a new carbon-carbon bond here, you also have to join this carbon here to this carbon. Keep in mind at this point they do not limit you to any other reagent. The only limitation you have here is that you must start with this. Okay, from after you start with this here, then you could use any reagent you want. Okay, so we also need to form a new carbon-carbon bond here. So in this problem, we are forming two new carbon-carbon bonds. Okay, so what other reagent do we need? You're giving us Wittig. What other reagent do you think we should use here? We want to form another new carbon-carbon bond, giving us a secondary alcohol. Okay, borane does not give a carbon-carbon bond. Okay, we want to form a new carbon. Grignard, okay, very good. So now, once you made up your mind, excellent. Once you determine, okay, for this synthesis, I need Wittig, then I also need Grignard. Okay, let us see, how do we do that? Okay, so we say, okay, very good. Okay, so what do I do? I come here, I say, what is the sequence that I want to do here? Okay, perhaps I want to use my Wittig first. Okay, so Wittig. I use my Wittig. In other words, I want to form a new carbon-carbon bond here. So, and that will give me this. Okay, so you get that product. Now, if you see that, give me a happy face. Okay, so we are going to go from this ketone to, okay, using a Wittig. Okay, now, after you use your Wittig, keeping in mind now that somehow you want to form, do a Grignard. Now, what do we want to do with this Wittig product? Can anybody tell me, what do you want to do with this? What do you want to do with that? Okay. Oh, no, you don't want to hydrogenate. That would destroy it. That would destroy the double bond. Hydrogenation would destroy the double bond. You don't want to do that. Okay. Keep in mind, eventually you want to use a Grignard, right, to react with something that will give you a secondary alcohol. Okay. What compound does Grignard react with to give you a secondary alcohol? What class of compound is that? What class of compound does Grignard aldehyde? Excellent. In other words, at this point you say, okay, since I want to form a secondary alcohol here, I want to convert this carbon here to an aldehyde. Okay, so therefore, if I want to do that, what reagent do I need to do that? What reagent do I need to do that? How do you make aldehyde? That's the next question. How do you make aldehyde? Okay. How do you make aldehyde? Okay, maybe I'll give you a hint. What does a PCC and desmartin react with? Okay, how do you make, what class of compound do you need to, that do we need? A primary alcohol. Excellent. So if we need to transform this to a primary alcohol, therefore, what reagent do we need to transform this to a primary alcohol? In other words, hydrogen has to go here, OH has to go here. Okay, what reagent do you need to do that? Okay, we want to transform this. Excellent. Borane. Okay, step 1, borane. So you guys, you need to know this reagent. Step 2, hydrogen peroxide in basic medium. Okay, and that will transform a carbon-carbon double bond to a primary alcohol. Because what this reagent does is to add the element of water, which is hydrogen and hydroxide, across a carbon-carbon double bond in what we call anti-Markovnikov addition of water. That's what this is doing. Okay, so this reagent is an anti-Markovnikov addition of water. And what do we mean by anti-Markovnikov addition of water? That simply means the hydrogen. Okay. Okay. Let me say. Okay. Yes. Okay. Now the borane. This is not what you need for this. Oh, yeah, that is correct. Okay, borane. Yeah, anti-Markovnikov addition of water. Sorry about that. Which means that the hydrogen, for the anti-Markovnikov addition of water, which means that the hydrogen will go to the carbon that has less hydrogen, and the OH goes to the carbon that has more hydrogen. That is anti-Markovnikov addition of water. Okay, so therefore, what is the product we get here? Okay, notice here hydrogen goes here, we have hydrogen here, and the OH goes here. That is the anti-Markovnikov addition of water. Now, before we complete this problem here, supposing we want to do a Markovnikov addition of water. Supposing I wanted to get the hydrogen to come to here and the OH to come to here. What reagent do I need for that? Since we are doing a review now. What reagent do I need if I want to do a Markovnikov addition of water to this here? Oh, okay, very good, excellent. Mercury, okay, very good. For that you need mercury acetate. Okay, in mercury acetate in water, and then that is step 1, and then step 2, you add sodium borohydride, followed by step 3, hydrogen. Okay, that is if you want to do the Markovnikov addition. So this will give you Markovnikov addition of water. Okay, so anyway, in this particular instance though, what we want is anti-Markovnikov addition of water, and that is why we use this reagent here. So now we get this primary alcohol. So now what is the next thing we are going to do? Once we get the primary alcohol. Okay, once you get the primary alcohol, what reagent do we need now? Okay, keep in mind this is where we want to go eventually. PCC, excellent, excellent. Okay, that's Alexis, very good. Okay, so now you want to do PCC. PCC. Okay, so that will give you this here. So this become, okay, we are almost there. So finally, how do we get to our final product? We now want to go from this aldehyde now to this final product. What reagent do we need? Oh, Grignard, excellent, excellent, very good. Now I want to use a Grignard. Okay, very good. So let us say now we are going to use Grignard. Okay, the Grignard will be, this part will be coming from the Grignard. Okay, so we have this Grignard here. And that is step 1. And then step 2, to add the hydronium ion. Okay, so at this point we react this Grignard here with this aldehyde to give this final product, which is a secondary alcohol. Okay, so now you see what we've done here. How many steps have we used? One step. Okay, this is 2. This is 3. Let's say step 1, 2, 3, and 4. So we have used 4 processes here to go from this starting material to the product. But the only way you could do this is when you know those individual reagents, and that is why it is most important that you know those reagents. Okay, if this is clear to you, give me a happy face. Okay, keep in mind the first thing you need to know your reagents. Okay, very good. Let us go to here. Okay. Okay, if your mic is working and you have not spoken tonight, can you pick up the mic
Provide a mechanism
and
for
read
the
this question for us?
nucleophilic reduction of an ester by lithium aluminum hydride followed by dilute acid to give an alcohol.
Okay, thank you. That's Annette Levy. Okay, thank you. Okay, so now what this question is asking you to do is to provide a mechanism for the nucleophilic reduction of an ester by lithium aluminum hydride followed by dilute acid. So in this case, what they're simply giving us is a generic, we have a generic ester here, just any ester, okay? And they want you to give the reaction mechanism. Okay, so we have this. And as you guys know already, that the sodium borohydride or lithium aluminum hydride, what do they do? What do they do? What do they provide? Let me ask that question. What does each one of them provide? Hydride. Okay, excellent. Okay, just think of this as providing hydride. Okay, so therefore, what do you have? You have this. That is your hydride. Now, you notice the similarity between the mechanism we are going to give you and the mechanism for the Grignard reagent. Okay, if you look at the Grignard reagent, for example, if you look at this Grignard here, let us take a very simple Grignard. Now, what does that Grignard provide? All it provides is supplies for the reaction is this negatively charged alkyl group, okay? Okay, it's what we call a carbon ion. is negatively charged alkyl group. That is, so this is very similar to the hydride. So let us follow this process here. You will see the similarity between all of both of the reaction mechanisms. So what happens here? You have a carbonyl. This is going to act as a nucleophile. The hydride acts as a nucleophile, attach this carbonyl, and in so doing, the pi electron goes to oxygen. Okay, the same thing will happen if this methyl anion, if it reacts with the carbonyl to form an intermediate. Okay, so you form this intermediate. Keep in mind here, initially you do have non-bonding electron here. So what you, let me change the color of the pen, make it a blue. So you have that here. Okay, so if you are using the Grignard reagent, okay, instead of the hydrogen here, the methyl will be here, or any alkyl group coming from the Grignard. So follow this very closely, because this mechanism are basically the same. Okay, so now what happens? Okay, what is going to happen? Now we form what we call a tetrahedral intermediate. Okay, we form a tetrahedral intermediate. Now, what is going to happen to this here, to this intermediate here? What is going to happen? Anybody knows? What is going to happen? Very unstable. What is going to happen? Any idea? Any suggestion? Okay, the group. Okay, the toxide, the methoxide will leave. Okay, but yes, that is correct. Okay, very good. But before the methoxide leave, you have to reform the carbonyl. Excellent, excellent. Okay, so you reform the carbonyl. So this comes here to reform the carbonyl, and in so doing, the methoxide will leave. And then what do you get here? We get this here. And using a blue pen. Okay, so what we have an aldehyde. We have an aldehyde, okay, as your intermediate. Now, supposing this was, I ask you to give me the mechanism of a Grignard reaction with this ester. At this point, right here, what class of compound do you think we will get? Think about it. Methyl will now be, hydrogen will now be methyl. What class of compound will you get at this point? What class of compound? Will it be an alkene? Will it be a ketone? Will it be a ketone? Methyl ketone, exactly. Because keep in mind, that is what I want to show you, the similarity between these mechanisms. They are basically the same type of mechanism. A nucleophile attacks the electrophilic carbon to form the tetrahedral intermediate, and then you reform the carbonyl. In this case, you form an aldehyde. In the case of the Grignard, you form a ketone. So at this point, the aldehyde is also very reactive. So another hydride comes in. Another hydride comes in. Okay, what does the hydride do? Comes in here, attack the, what does the hydride do? Can anybody tell me what does this hydride do at this point? Okay, attack the no, this is the nucleophile. The hydride is acting as a nucleophile. Attack the carbon of the carbonyl, exactly. So at this point, we are going to get a nucleophilic addition reaction. Okay, remember nucleophilic addition reaction is here. Adding to that, this comes here, and then we form this intermediate. This time, we have this hydrogen here, another hydrogen here. And so, finally, therefore, this is when we now add our dilute acid. Once you now add your dilute acid, you add your dilute acid. Once you add the dilute acid, and what do we get? This alkoxide here, negatively charged oxygen, coming here to grab this proton from the hydronium ion, releasing the electron to this oxygen. Okay, and then you form your, in this case, you form your primary alcohol. Okay, this hydrogen is coming from the hydronium ion, and of course these two hydrogen here, oh no, sorry about that, this should be blue. Okay, these two coming from the lithium aluminum hydride. Lithium aluminum hydride, okay? So the hydride is coming from these two hydride, this here, right here, and right here, coming from the lithium aluminum hydride, and then finally this hydrogen here coming from the hydronium ion. And that is why we say you have to indicate step 1, addition of the lithium aluminum hydride or sodium borohydride, and then you then say step 2, addition of the hydronium ion. And the same thing if you are using a Grignard, okay? So the mechanism is basically the same. Okay, so now let us go to, okay, number 13. This question number 13, I want to wait until class tomorrow to do this. Okay, I want us to do this in class tomorrow when I will be seeing you guys face to face. Okay, so remind me to do that tomorrow. That's question number 12. Okay, number 13. Let us do 13 and 14, and then we call it a day. It's already past 9 o'clock. Okay, if your mic is, if you have not read a question for us today and your mic is working, can you pick up the mic and read this question for us?
Provide a mechanism for the following transformation. Assume there's a dilute acid in the reaction mixture.
Okay, thank you. That's Christy Premier. Okay, very good. Okay, that was good, Christy. Okay, so now this question says provide a mechanism for the following transformation. Assume there is dilute acid in the reaction mixture. In other words, what they are telling us here, assume that you are this here, okay? Okay, now, what is going on here? What is happening here? This is another reaction mechanism problem. If you look at what we have here, what are we adding here? In essence, look at this. We are adding the element of water. If you look at this molecule, right here, there is hydrogen here, okay? But so therefore, if you look at the product, okay, that hydrogen is still there. Okay, now we have right here. Let me use green. Now we have this hydrogen here, and in addition to that, we have. Let me also use green for this hydroxy group. Okay, so what are we doing? In essence, we are adding the element of water across this carbon-oxygen double bond, okay? But the only way we can do this is because we have a conjugated system. we have a conjugated system. In this particular instance, the conjugated system is a conjugated ketone. And because of that, in essence, we are going to be able to add the hydroxide here, okay? We are going to add the hydroxide here and then the hydrogen here. And how does that happen? Now, if you take a look at this, take this out of here. Okay, if you take a look at this, we have hydronium ion here. The first thing that happens, you have a carbonyl, because keep in mind what we want to do here is to explain how we got this product, okay? So therefore, you want to be able to say that this carbon here is electrophilic, because eventually what you are going to do, this water here will be acting as a nucleophile. This oxygen or water will be attacking this. In order for that to happen, that means this carbon must be electrophilic. In other words, it must be positively charged. How does that happen? The only way that happens, if you start off, with the hydronium ion. Okay, so we say this here, this non-bound electron from oxygen comes here to grab this proton here, and thereby will release electron to this oxygen here. Now we form this protonated intermediate, in which we now protonate the oxygen of the carbonyl. Now this is now positively charged, okay? And we see how the double bond right here, and this is here. Now if you take a look at this, we could write a resonance structure for this here. If I move this electron to here, follow this very carefully, there will be a positive center right here, and as a result of that, I will move this pi electron to form a pi bond between this carbon and this carbon, and in so doing, what do I have? I now have this. Okay, these non-bound electrons are now here. Now the double bond is now here. Now the positive charge is now here. And that is possible because this carbon here is conjugated with this carbon-oxygen double bond. So we are able to move the pi electron to here, thereby making this carbon positively charged. Okay, this is still here. So this carbon now becomes electrophilic. Become electrophilic, or become an electrophile. Okay, at that point, now the water comes in, acting as a nucleophile. Okay, using this pair of electrons here, now attack this. Okay, attack that. When it does that, what do we have? We have this. Okay, this is still here. And now this water is here now. Okay, I want to use a blue pen. Okay, so now this is positively charged. Of course, only one pair of electrons is left here. Now, once we do that, this molecule now, keep in mind we are going to here. This molecule now this molecule will reform, because keep in mind what you have now, this is an enol. Remember what we told you about enol are very unstable. They rearrange very easily. So this will now rearrange to reform the carbonyl. And when that happens, okay, by the way, the material is still here. This material is still here. When that happens, now this pi electron here, instead of coming here, if it comes here, it will displace the water, and then we go back to here. That is not what we want to do. So instead of doing that, to come to this carbon right here, the pi electron comes to this carbon right here. Okay, so what do we have? And I have this. We have this here. Okay, we have that here. Okay, and in so doing, we are also going to be losing the proton. Okay. And this is now going to be here. And this is still here. And this is here, okay, positively charged. Okay, now see what happens now. The proton that we've lost here, this proton here, keep in mind the proton that is right here, will simply now come in here to attach itself to this carbon here. And then what do we have? We have this. See how this here, and that proton is still there, and we see how this here, and get rid of this here, it doesn't get on the way. Okay, so this is still positively charged. Okay, so at this point, what do we have at this point? Keep in mind, we have water in the system. This water that we release right here, okay, because when we protonated the initial carbon, oxygen of the carbonyl, so that water, we could simply imagine that we use that water now. What does it do? Come here to grab the proton from this protonated alcohol, thereby releasing the, and that is how we get to here. So the point here is, whenever you are doing the reaction mechanism, it's almost as though you are doing electronic bookkeeping. Electronic bookkeeping. In other words, you need to take account of all of the electrons and also take account of all of the atoms. So I would say electronic and atom bookkeeping. Everything in the molecule you need to account for, because the question here that they're giving us here to explain how we got this by the reaction of water in the presence of dilute acid, starting from this molecule here. So this is one way in which we actually get to know to what extent does students know their organic chemistry. Anyway, so this is all about reaction mechanism. Before we leave, I do want us to do number 14. Okay, we did this in class already. Number 14, I think we did this in class already. But I do want, okay, Mashake, can you go ahead and read this first?
cyclohexanone reacts with 2 moles of methanol with acid catalase to form a keto. Provide the mechanism for the reaction.
Okay, very good, and thank you. Now, I'm not going to do this, but I will do something similar to this, just to show you, okay, because essentially what they say this year, I think we did this in class, so you may want to review some of those webcasts that we did earlier. Okay, you take cyclohexanone, and essentially they say that if you take 2 moles, turn your mic off. If you take 2 moles of methanol in the presence of acid catalase, this is the catalase right here, that we get this. Do you guys want us to go through this again? Yes, sir. If you want us to go through it, give me a happy face. Somebody have their mic off. Turn your mic off. Okay, you want us to, okay, you want us to do that. Okay, in this particular instance here, we are going from this ketone here to a ketal. Okay, so let us see here. What will be the mechanism? Let me write this here, get this out of the way. So this is the ketal that we want to make. Okay, from cyclohexanone. So you guys want to, okay, we do this and then we call it a day. Okay, so I'll now make myself some room to take this out of here. Okay, so we start with the cyclohexanone. In the presence of let us say that we have HCl here as a catalyst, okay? Okay, so what do you think, what will be the first thing that happens? Anybody has an idea? What will be the first thing that happens? Okay, oxygen attacks the proton. Excellent, very good. Oxygen attacks the proton, okay? Very good. So this oxygen attacks this proton here. We'll grab the proton and then we'll release this chloride. Okay, very good. So now we form this. So this oxygen becomes positively charged. Now, at this point, the methanol, okay, let me use a different color pen. The methanol comes in. The methanol, the oxygen of the methanol will now act as a nucleophile. In doing so, it will attack this electrophilic carbon here. Now, the reason why we use the acid to protonate the reason why we protonate this oxygen is to make this carbon very electrophilic. Because the moment you protonate this oxygen here, the electron wants to now go to oxygen, thereby making this carbon very positive. And that is why we generally do this reaction under acid catalysis. Okay, so what happened here? So now you have this. Okay, when you do that, this electron also will now go to oxygen. Okay, so we have this here, this here, this here. Now we have this oxygen is now attached to here, hydrogen is here, and this is here. And this is also now positively charged. Only one pair of electrons is left. Now, at this point, this could happen. This could happen. Let me take this here. Remember the chloride that we formed here, this chloride here. Okay, we release that. Okay, that chloride will simply come here. Remember that the hydrogen chloride in the first place was used as a catalyst. So we are going to regenerate that. So that comes in. This is negatively charged. So this comes in to grab this right here. Okay, and so doing we release the pair of electrons to oxygen, and now we form this. And this here. Okay, now we form HCl. You see, we have regenerated the HCl that we started with because it was used as just as a catalyst. Okay. Okay. So at this point, we have formed this product here. This is what we call an emi-ketal. This is what we call an emi-ketal, okay? In the emi-ketal, that comes from a ketone, the addition of an alcohol to a ketone. You get an emi-ketal. You see here, in the emi-ketal, you have this carbon here is attached to the alkoxy group and an hydroxy group, okay? That is the carbon coming from the carbonyl of a ketone. So that is the first thing you get. Now, this emi-ketal, since we have excess alcohol, this emi-ketal could now further react with HCl, okay, just as it did before. Okay, this here, this oxygen here, come here, grab this proton, releasing these two. Okay, so now what we now have a protonated emi-ketal. Okay, and on this side, now does anybody know what will happen at this point? We now have this molecule here, this intermediate here, okay? Does anybody know what will happen at this point? Anybody has an idea what will happen? Keep in mind, this is where we want to go. Water leaves, exactly. We are going to lose water because water is an excellent living group. Okay, so the water will break away. And once to do that, we are now going to form a carbocation. Okay, you now form a carbocation. So now, what do you think is going to happen now? What will happen next? What will happen? This is where we want to go. What will happen next? We form a carbocation. Anybody has an idea? This is where we are going, right here. What will happen next? Any idea? Okay. Keep in mind, we need to explain how we got to this molecule here. Okay. So what is, okay, very good. The methanol will attack the carbocation. Excellent. Excellent. So now the methanol will attack the carbocation. Methanol will now, another molecule of methanol will act as a nucleophile again, attack this carbocation. Okay, and then what do we get? Get this. Okay, so now we form this protonated ketal here because we are almost here. Okay, so therefore, so what is going to happen now? Keep in mind we have this in solution. The chloride is in solution right here. So what is going to happen now to generate the final product? We have this in solution right here. What will happen? Okay, the chloride attack the chloride will attack the proton. Exactly. That is what happens. So now the chloride comes in and grab the proton, and the proton, of course, once the chloride grabs the proton, we are going to release this electron to oxygen, and therefore we form the final product, which is this here. From that final product. Now, if you see that, give me a happy face. If you see that, give me a happy face. Okay, now, supposing, before we leave, just I want to give you a teaser here. Supposing I do this. Supposing I do this. I want you to think about this. You go home and think about this. Supposing I do this. Okay, supposing I do that. Okay. And I say, give me the mechanism for that reaction. Oh, by the way, what class of compound will you call this? What this product here? What class of compound will you call this product here? What class of compound will you call that? Okay, this will be, keep in mind, this is coming from an aldehyde. No, that is not an ester, no. This is an hemiacetal, okay? This will be an hemiacetal. Okay, what have you done? We have essentially added one alcohol to a carbon-oxygen double bond of an aldehyde. That is essentially what we've done here. That is similar to what we did in the case of cyclohexanone. Okay, remember when we took cyclohexanone, right? You see the similarity here? Remember the first thing we did, if you take 1 mole HCl, if you do this, this is an ketal because it is coming from a ketone. So this here is a cyclic acetal. Okay? So supposing I tell you to give me the mechanism of this reaction, right? This one here. Supposing I tell you to give me the mechanism of this reaction. Okay? What do you think is going to happen? Okay, let me number this carbon here to give you some help. Let's take all this out of the way. Okay, let me number this. Let us say this is 1, this is 2, this is 3, this is 4. Okay, so therefore I will say this is 1, this is 2, this is 3, this is 4. Okay, so what do you think will happen? Anybody has an idea? The first thing that happens, based on the mechanism we gave you just a few seconds ago, what is the first thing that happens? Oxygen attacks the hydrogen. Which oxygen? Which oxygen? The oxygen of the carbonyl. Okay, excellent, excellent. Okay, very good. That is similar to what we just did. Okay, and that is why, you know, the critical thinking, that's how we force you to think critically, because this is similar to what we just did. So now, this here just comes here. I'm going to start this and allow you guys to finish this at home, okay? Okay, so this here, and then, like I said, this is a teaser to all of you, so, and then you get this. Okay, now you get that. Keep in mind this oxygen here, you have this here, okay? So this is where I'm going, as far as I will go with you in terms of the mechanism. Now I want you to now complete the mechanism and give this product, okay? Okay, so that is the assignment I have for you guys. It is similar to what we just did, but simply just follow this very closely. The hint here is that this oxygen will be acting as a nucleophile. Okay. Is there any question before we leave today? We spent 90 minutes already. Is there any question? Okay, folks, we have come to the end of our session. What I will do, I will stay behind for another 5 minutes in case you want to ask me some questions of the recording. So I'm going to turn off the recording now, and then for those of you who are leaving right away, enjoy the rest of your evening, and those of you